Okay, so when I hand out your gold sheets, you will see that on both today and tomorrow's assignment, I'll give you some problems from the book from 7.1 and 7.2. So both section 7.1 and 7.2 are two variable systems solving with substitution or elimination. As I said Friday, I don't think we need to spend an entire day in class doing that. Okay? So when I hand out your gold sheet after our notes, if okay, if you need more practice with substitution and or elimination, I give you some non-bolded problems both today and tomorrow if you need a couple more problems to practice. Okay, so you need to decide for yourself, do I need more practice with this? Some of you may feel fine about like 1 through 4, but want some more practice on problems like 5 or 6, then choose those out of the unrequired problems. Okay? Because guess what? Those are probably going to be more of the ones you'll see on the quizzes and tests. Okay? So just an FYI for you there. Okay? All right. So today we're going to talk about 3 variable systems. Now, when we're talking about 3 variables, we've introduced a third dimension. Okay? We have a z, which means we have an x, y, z axis. Now, you have not graphed in 3 dimensions. However, you know, or you did at one time, that a linear equation in 3 dimensions represents a plane. Okay? A linear equation in 3 dimensions represents a plane. So, here are our 3 or more than 3, 5 options, okay? Now, I don't expect you to draw these. I just want you to be aware of the different cases that we're going to have graphically. We talked up here when we were going over your worksheet, we could have 2 lines in 2 dimensions that intersect, that are the same, or that are parallel, okay? We still have kind of that same concept, but we have a couple more options, okay? More times than not, you are going to see 3 planes intersect at a point. Okay, and so those are problems like number 7 and 8 on your pink worksheet. Okay, however, we could get an infinite number of solutions. The thing is, they could look 2 different ways. We could either have 3 planes intersecting at a line, which means we have an infinite number of solutions, okay, because there's an infinite number of points on that line. Or we can have an infinite number of solutions because our 3 planes are the same plane, okay? And we're actually going to look at this case today, okay? We could have no solution, but that could look slightly different. We could have parallel planes, much like we have parallel lines in 2 dimensions. Or we could have the 3 planes all intersecting, just not simultaneously, and so they don't share any points in common between all 3. Okay? So what I want to do is I want to go over number 8 from your worksheet. Okay? Let's just go over the process and how to solve this equation. Okay? Now, some of you sort of remembered from last year. Some of you, it was tough to call back. So we're just going to all go through it together. What I want you to do is I want you to use elimination until you get this down to 2 variables and 2 equations. Okay? So look at the variables x, y, and z. Pick a variable to eliminate. Which variable would you like to eliminate? Z. All right. So if we want to eliminate z, then maybe we can multiply this third equation by -1 and use it with the second equation. What do you think? Sound good to you? All right, so I'm going to write our second equation and negate the third equation. Oh, can actually negate it. Okay? What I did this just there is a very easy mistake to make. Please make sure you're distributing to all terms in your equation. Okay? All right. So if we add these 2 together, What are we left with here?
Negative 2x minus y equals 0.
Negative 2x minus y equals 0. And what I'm going to do, just for our reference, is I'm going to box that because I know we're going to need to come back to it. Okay? Don't feel like you have to box it, but I'm going to so it sticks out up here. Okay? Now, we need to do that again with two different equations. So which two would you like to pick to eliminate z for a second time? There's no wrong answer. Sure, the first and second. So if we want to eliminate z from the first and second equation, we can multiply the first one by negative 3 and the second one by 5. Would that make our z's opposite? Yeah. Okay. So, probably wrote too big. We'll do it right here. So we have negative 9x plus 15y minus 15z equals negative 3. And we have 25x minus 10y plus 15z equals 0. All right. What are we left with here?
14x plus 5y equals 3. Negative.
All right. So now yes. 16x? Okay. Now I will tell you, you will have calculators in your hand for this test. Some of you that might make you feel a little bit better because we haven't really had that for a while. So you will get calculators. I don't feel like you need to rely on your calculators, but know that you can refer to your calculator if necessary. Okay? All right, so now we have whittled this down to two equations with two variables. Do we know how to do those? Okay, I think we all would say that we're fairly confident on two variable systems. So look at those two equations that I have boxed. How would you like to solve that? Which method, elimination or substitution? There's no wrong answer. Elimination, okay? Do you want to eliminate x or y? All right, so we could multiply this first equation by 5, right? So that we have negative 10x minus 5y equals 0. Our second equation is 16x plus 5y equals negative 3. And when we add those together, we get 6x equals negative 3. Or x equals 1/2.
Negative.
Negative 1. Thank you. Okay. Now, should I take this negative 1/2 and jump all the way back up here to the beginning? No. No. Let's come back. We're still here in these two equations with x and y. Let's pick one of these and plug negative 1/2 in. Which one might be the easier one to plug into? This first one or the second one? I would probably pick the first. Probably doesn't matter. So what we have is negative 2 times x minus y equals 0. So this becomes 1, and I can add that y over. Y equals 1. Okay, now that we have figured out those two variables, we can go back to the very beginning and plug those two in for one of the original three equations. Doesn't matter which one. It does not matter which one. Do whichever one you think would be easiest to work with. So, I'm asking you, as my first hour class, which one would you like to choose?
The second one.
The second one. Okay, 5x minus 2y. So we have 5x minus 2y. What was the rest of it?
Plus 3z.
Plus 3z equals 0?
Yep.
Okay. So we have negative 5 halves minus 2 plus 3z equals 0. Negative 5 halves minus 2 would be the equivalent of negative 9 halves. Do you agree? So we have 3z equals 9 halves. When we divide by 3, we get z is 3 halves. Okay. Once you have solved for each of the three missing variables, I need you to write it as an ordered triple. This is the coordinate in 3 dimensions that our 3 planes are intersecting at. What questions or clarifications do you have about this example? Okay. Do you remember doing this last year? Yeah. Okay. Let's talk about a couple things, because I think these, more importantly, compared to the 2 variable systems, there's a lot more room for error in these problems with 3 variables. Okay. Please be very careful and take your time when you're solving these. Okay. Like up here, I would always write what I was multiplying by. Okay, so I had that visual of, okay, I'm distributing that negative 3 to that first equation. I'm distributing that 5 to that second equation. Write it so you can visualize it, okay? Be organized with your work. If you're all over the place, you might lose some equations, you might lose some coefficients, you might lose some signs, positive, negatives, okay? Now, you may have gotten to this answer and thought, ugh, I'm just really not sure if that's right. Negative 1/2, 1 3/2. Okay? How can you know that you are right? Plug it in. All right? If we plug in, is it negative 1/2, 1 3/2? Let's just, for instance, plug it in right here. 7 times negative 1/2 minus 1 times 1 plus 3 times 3/2. Does that equal 0? Okay. Negative 7/2 minus 1, which is like 2/2, plus 9/2, that equals 0. Okay? You don't even have to write it down, but just mentally doing that or plugging it into your calculator, you should know on a quiz or test or your homework if you're getting the right answer, because they should satisfy each equation you have up there. All right, let's do this process one more time. Go ahead and write this equation down. Okay, what I would like you to do is have just like a 15-second conversation. What variable as a pod would you choose to eliminate? All right, pod number 3. That is you fellas right here. Which variable would you choose to eliminate?
I would get rid of Y and Z.
Y and Z. Okay, I see where you're seeing that, but let's just focus on one variable, okay? Because it's going to happen in one equation, but not another. That elimination, that's going to happen. Okay, so Y or Z? Z. Okay, so let's go ahead and eliminate Z. Is X, Y, or Z a wrong choice? Everyone's going to do these problems different, and that is fine. Okay, so what Chris sees is this right here. If we combine the second and the third equation, both the Y and the Z are going to cancel out, right? If we add those together, we get 6x equals, 5x equals 5. Okay? Both variables end up canceling out. Now, that's fine. That's not going to happen very often, but we still need to go through the process of eliminating that third variable a second time. Okay? So, would you like to work with the first and second or first and third? Liam, what do you think? First and second. Okay. So RZ is opposite in the first and second. No. So in order to get them opposite, we're going to have to multiply one of them by -1. So we can take the first equation, x plus y plus z equals 6. -2x plus y minus z equals -3. Okay. So -x plus 2y equals 3. Okay. Now, because we had two variables cancel out, this is going to make our substitution process easier for this. Okay, what do we know when we look at this first set of elimination? What do we know? We know x is 1. Okay, so we can go to here and we can figure out what y is. -1 plus 2y equals 3. Y equals 4. So y is 2. All right, so now we go back to our very first tier. Okay, we kind of have like two things happening, right? We have this first tier where we have 3 equations. Then we do elimination twice to get to the second tier where we have 2 equations, 2 unknowns. We solve that, and we can come back to the original. All right? Eli, which one do you want to plug back into? Sure, the top one. So x plus y plus z equals 6. What is z? Well, that's a nice answer, huh? Our coordinate is 1, 2, 3. Okay. Does it work in each equation? 1 plus 2 plus 3 is 6. 2 times 1 minus 2 plus 3 equals 3. 3 times 1 plus 2 minus 3, that equals 2. Hey, you don't have to show me that you checked it, but go through the process of checking it more for a satisfaction of, okay, I really do have the right answer. Okay. All right, this is our last example. I want to look at what happens when we have that case of infinite solution. That looks weird? Okay, so this is a problem a lot like number 7. One of the equations already has a variable eliminated, right? So let's use that to save us some time, okay? Let's eliminate y. Cool. Our second equation already has y eliminated. Okay? So now let's pick the first and third equation and eliminate y. So then we really are only doing it once. So what would we need to multiply that first equation by? -3. So we have -6x minus 3y plus 9z equals -12. -2x plus 3y minus 13z equals -8. So we get -8x. Uh-oh. Did I do that okay? -8x minus 4z equals okay. So here are our two equations. You're giving me a look like, what are you noticing? What? Okay, so if we want to eliminate, let's say x, we would want to multiply this one by 2. In that case, we would get 8x plus 4z equals 20. And when we add those together, we get our case of 0 equals 0. Okay, now here's the deal. In a 3-variable system, you can't just say infinite solutions. Okay? Now, because we have 2 different things that could be happening. These 3 planes could be intersecting at a line, or they could all be the same plane. If it's the case that they're all intersecting at one line, we need to describe that line. Okay? Now, have I taught you how to write the equation of a line in 3 dimensions? No. Have I ever taught you anything about 3-dimensional slope? There is no such thing, okay? We're not going to write the equation of a line like y equals mx plus b, okay? We don't have 3-dimensional slope. But what we're going to do, we're going to write a coordinate based on the number A. Okay, where A we can plug anything to and represent that line. So instead of writing the equation of a line, we're going to write a coordinate in terms of A. Okay, so once you get to this point, I want you to pick a variable and set it equal to A. Since we were working with X and Z here, I want you to pick one of those. Z equals A. Okay, and we're going to write each variable in terms of A. Okay, and I'll show you what the answer is going to look like just here in a moment, so bear with me. So if we go back up to this blue equation right here, 4x plus 2z equals 10. We would have 4x plus 2z, it's now A, equals 10. And I want you to solve for x. Okay, we want to figure out what x is. So we have 4x equals 10 minus 2a. When we divide both sides by 4, we would get x equals 5 halves minus 1 half a. Then we would need to go back and plug x and z in to one of the original equations to figure out y. We're still going through the same process, we just have some a's involved here. Okay? So let's see. I think the first one looks nice, don't you think? We would have 2 times x plus y minus 3 times z equals 4. Okay. So now we just need to solve for y. It's going to take us a couple steps, so just be patient. We have, if we distribute this, 5 minus a plus y minus 3a equals 4. So we have 5 minus 4a plus y equals 4. So then to solve for y, we would subtract that 5 over to get negative 1, and we would add that 4a over. Okay? So the line that these three planes are intersecting at could be represented this way. So instead of having to describe three-dimensional slope, we write our variables in terms of A, and then we can plug in any number for A and have a point on that line. So what we're doing is, yes, we have infinite solutions, but we're writing what those infinite solutions look like. They're a unique set of infinite solutions, right? We could have different lines in 3 dimensions. So this is the line that these three are intersecting at. So this is pre-calculus, right? We do some topics that we already know, and then we go a little bit further with them, right? You've done 3 variable systems before, but you need to brush up on them. However, then I introduced you to what happens when we have infinite solutions. You need to make sure that you practice these in your homework. Okay, these are the new things that we talked about today compared to last year. Make sure you practice them. Okay, all right, so let me get this stopped here.